Welcome back to The Explainer. Today, we're jumping straight into Chapter 2 of our journey through everyday geometry. You know, geometry often feels like it just lives purely inside textbooks, right? Just a bunch of rigid rules to memorize. But today, we are taking it right off the page. We're going to translate some fun, hands-on activities into the foundational math that is quite literally hiding right in front of us. We're talking about the shapes, the lines, and the angles that actually build our physical reality.
Okay, let's dive right in. Just take a look at the shapes of these incredibly common items we see every single day. A CD, a wall clock. I mean, way before we ever learn the word geometry in a classroom, our brains are already processing these perfect, continuous curves. They aren't just household objects. They are actual, physical manifestations of literally one of the most important geometric concepts in all of mathematics.
Look at the top of this beautifully patterned tin. It brilliantly illustrates that before we even touch a ruler or, a protractor, mathematical shapes are already framing our physical world. It's in function, it's in everyday art. Think about it. The precise mathematical curve of that lid is exactly what allows it to seal perfectly. Section 1, Defining the circle, from objects to math. Let's see how we go from everyday items to actual math.
If you want to see this mathematical magic in action for yourself, try this. Grab a simple coin, a teacup, and maybe a saucer. If you place them down on a piece of paper and carefully trace around their edges, you can physically feel how these shapes are formed. You're not just doodling. You are literally capturing the geometry of a 3D physical object and transferring it onto a flat, two-dimensional plane.
So what's the crucial takeaway here? Well, it's the definition itself. That complete curved line you just drew around the cup or the coin, that specific unbroken boundary is what we officially define in math as a circle. And this is incredibly important to note. The circle is the continuous line itself. It doesn't matter if it's the size of a tiny coin or a massive towering satellite dish. A circle is a circle.
Actually seeing this process in motion is just so fascinating. Look at how physical items of completely different sizes, when traced, all yield this exact same mathematical concept. The physical scale changes, right? But the fundamental geometric properties, they remain perfectly, absolutely constant.
Moving on to Section 2, Finding the perfect center through the folding experiment. So how do we find this perfect center? Well, we can make what mathematicians call a circular lamina, which honestly is just a fancy term for a flat cutout circle. By cutting out our drawn shape and repeatedly folding it exactly in half along a bunch of different lines, we're actually creating a physical proof. Every time you fold it so the curved edges match up perfectly, you create a straight fold line right across the middle of the shape. Let's look at the result of all those folds on this blue circular cutout. After folding it multiple times across different axes, take a close look at where those dotted fold lines meet. Every single one of those straight lines perfectly intersects at one exact spot right there in the middle. No matter how you folded it in half, they all cross at the exact same point. And this brilliantly illustrates our core geometric truth. The distance from that center intersection point we just found to absolutely any spot on the curved outer edge is exactly the same. This property, being perfectly equidistant from the center, is the foundational rule that makes a circle, well, a circle. All right. Section 3, Inside, Outside, and On. Let's talk about positions. Imagine standing right in front of a circular dartboard. When you throw a dart, where it lands perfectly demonstrates spatial positions in geometry. So, that dartboard, it isn't just a fun game, it's a real-world map of geometric space. The crucial point here is the clear distinction in spatial relationships. And hey, it happens to map perfectly to typical dart scoring rules. For example, if your dart lands precisely on the circular boundary line itself, boom, you get 10 points. If it lands anywhere within the space it encloses, inside the circle, you get 5 points. But if you completely miss that enclosed space and land outside the circle, yep, you get 0. Inside, outside, and on. You can easily test this exact principle yourself on a scrap piece of paper. Just draw a circle using that coin from earlier. Now mark an X inside the circle, place a little dot directly on the line of the circle, and then draw a check mark completely outside of it. This super simple exercise physically maps out how we define space in relation to any geometric boundary. Section 4, Angles, Verticals, and Horizontals. Time to move beyond circles. Okay, picture a standard analog clock on the wall. At exactly 3 o'clock, the minute hand is pointing straight up, and the hour hand is pointing directly to the right. Together, they form a perfect right angle. This 90-degree intersection is exactly equal to the sharp corners of the notebook you're writing in or the computer screen you're looking at right now. You know, it's kind of wild to realize that these so-called abstract right angles are physically everywhere. I mean, they are literally holding up our world. Two edges of a book cover meeting, the sharp corner of a teacher's desk, the corner of a classroom blackboard. Right angles provide the structure and the stability to the environments we rely on every single day. To understand spatial orientation even further, let's just use a regular old table to ground the concept. The flat top where you rest your arms or place your book, that is a horizontal plane. Meanwhile, the table leg plunging straight down into the floor to hold the whole thing up represents a vertical line. So horizontal goes side to side, and vertical goes straight up and down. Easy, right? Let's apply that directly to this everyday red box. Looking at it, we can instantly identify the geometry at play. We see the flat, horizontal plane of its lid, the straight, vertical lines of its sides, and those perfect right angles exactly where those planes meet to form the corners. And just like that, we've wrapped up Chapter 2. But I want to leave you with this final provocative thought. If you look around the room you're sitting in right now, how many circles, right angles, vertical and horizontal lines can you spot hiding in plain sight? Seriously, give it a try. Math isn't just trapped in textbooks. It's the invisible, structural framework of absolutely everything around you. Keep exploring, keep questioning, and I'll catch you on the next explainer.